the cross product of two vectors in space. The cross product of two vectors in space. Here we introduce a very useful tool in math, and particularly in analysis, the cross product. The cross product is helpful in terms of trying to find an orthogonal or perpendicular vector to two other vectors. We use the cross product in terms of trying to compute the so-called area of a parallelogram, and then also its technique is useful for computing the volume of a parallelopipe. The cross product is also useful for computing for a vector field to determining, say for example, whether or not a vector field is conservative, or looking at that vector field in terms of a total differential to determine if the total differential for differential equations, if that total differential is exact. If it's a vector field, we look at that more so in calculus 3 to determine whether or not the vector field is conservative, which means the same thing as exactness for differentials. We use the cross product to get that. The cross product is nothing more than a trumped up case of the determinants. That's a pretty good phrase. I like that. Anyway, the definition of the cross product of two vectors in space, the word space simply means the Euclidean third space of length, width, and height. Let's take three vectors in the space. Well, here two vectors in the space. And so the cross product here is given by this formula, of which I don't know about you, but I never memorized it. It is no more than the determinant of these two vectors with respect to their positions with the x, y, and z axis. So here, if you know about the determinant from Math 112, or when I was in high school, we looked at the determinant of a 3 by 3. This is all you're doing. So I have the explanation here in the notes. You can feel free to look at that and go over it. But the way we do it is we take this determinant and we break it down with this 3 by 3 by taking the ith position. We take the I term and place it here, and we delete the ith row and column. And then you take the subdeterminant of the four items that's left. So the determinant of a 2 by 2 just becomes this the cross product. So it's u sub 2 times v sub 3 minus u sub 3 times v sub 2. That's here in this position. And then we alternate the signs. Is the signs for the minor that we call for the coefficient expansion, cofactor expansion, is plus, minus, plus, minus, plus, minus, plus, minus, plus. How do you get that? For the even position, the minor is positive. For the odd position, the minor is negative. So this is the first row, first column. So 1 plus 1 is 2 is even, so it's positive. This is the odd position. This is the first row, second column. So 1 plus 2 is 3, so it's negative. This position here is even, first row, third column. 1 plus 3 is 4, so it's positive. Right? And it doesn't matter which row or column you expand along, and you just keep that rule in mind. Here they are expanding along the first row, so they put the ith, the jth, and the kth terms there. So you come to the I, you delete the ith row and column. You come to j, so it's minus. Come to j, delete the jth row and column. See how they have it here for you? Oh, pretty cool. You can't beat the book. So delete the jth row and column, and then it's the determinant of the submatrix of those four entries. So here is u sub 1 times v sub 3, see that? Minus u sub 3 times v sub 1, right there. And then it's plus now, with that minor position of plus, negative 1 to the 1 plus 3 is negative 1 to the fourth, so it's plus sign. Delete here for k, delete the kth row and column. So then it becomes the determinant of the matrix. So it's u sub 1 times v sub 2 there, minus u sub 2 times v sub 1, right? This guy is that times that, and is this times this minus, we go in the opposite direction for the determinant. Now, some of you, I think in physics, and my good colleague over there, Dr. Goldman, who uses the side-by-side method or the arrow technique to calculate the determinant, that's fine. Whichever way how you want to find the determinant doesn't matter with me, as long as you get it. So again, the cross product is nothing more than the determinant of a 3 by 3, with the first row being the I, j, and kth position of those unit vectors. So the cross product is helpful. Here, this theorem is a very fancy theorem. 11.3 is just the algebraic properties of the cross product. I think 2 to take note of is that the cross product of u cross with v and the cross product of u and v and u, excuse me, if you reverse that, they differ by a negative. And so here, the cross product is not in what we would call commutative. The cross product does not commute. It commutes over a negative, if you will. And then the cross product of a vector with itself is 0. So I think those two are two of the properties to keep in mind. There's a problem that we can relate those properties back to work the problem out a little bit easier. Geometric properties of the cross product. If u and v are non-zero vectors in the space and they are adjacent, here's the diagram, u and v, and then theta is the angle that's between u and v. So some very neat things that you can pick up, that the cross product of u and v is perpendicular to both vectors u and v. So if you're looking for a vector that is perpendicular to u and v, you find the cross product, which itself is a vector, would give you an orthogonal vector to u and v. The area of the parallelogram is said to be the norm of the cross product of u and v, which is this here. This area is the same as the norm of u times the norm of v times sine theta. Now you don't get that or see it until you kind of look at this parallelogram and see if we can work that out and maybe sketch the proof of that to see why that's the case. And then the cross product of u and v is 0 if and only if u and v are scalar multiples of each other. So if u and v are scalar multiples of each other, that means that they are parallel. They exist within the same parallel plane. And then, like I've forestated, the area of the parallelogram having u and v as adjacent sides is the norm of the cross product of u and v. Now, if we expand on this to see if we can make some sense out of what's happening, I like to maybe just start from scratch so you can kind of see how it is possible to build this scenario. Oh, I need the one with the arrows. Wrong way. Left turn, Clyde. Go this way. So now the angle, I'm going to go ahead and draw the parallelogram from here. Just extend it out. No need for the arrows, but we got them there. We're not going to mess with it. So we have here this angle, theta. And let's see if we can highlight the height. Is it, give me the, so if this is v, and this side down here is u, you take the length of this side, and that's the magnitude. Take the length of this side, and that's the magnitude. Okay. I'm going to call this h for the height. Now, here the height can be determined by the sine of theta. Sine theta is equal to the opposite, which is the height, h, divided by the hypotenuse, which is the norm, v. Now, if that's the case, so the height is equal to the norm of v times sine theta. So the area of any parallelogram is the same whether it's a square or a rectangle. It's the height times the base. So here, this is equal to the base times the height. Well, the base here is the norm of u, and the height is the norm of v times sine theta. It gives us the area. So now, maybe this one makes sense. Well, let's see. These four properties are very important and most useful. Let's continue. What about, well, that's the area. What about the volume? Take the parallelogram and look at its third dimensional height, if you will. If you look at just the base in terms of how the vectors expand out. Let me go back and show that to you. If you look here, oh, I forgot to show you. I did forget to show you to illustrate number one. I need some help in my drawing. So we have these two vectors. And then we're going to have this vector that's perpendicular to both of them. Oh no, it's not what I want. It won't let me draw anymore. Suffering succotash. I think this is it. Good. That one. Well, let's try red maybe. So if this is u, this is v, so this is the cross product of u and v. Here, this guy is perpendicular to that one. And it's also perpendicular to v. So the cross product is said to be orthogonal to u and to v. Let's look at the volume. Here, the triple scalar product, the absolute value of it gives us the volume. Here we take the three vectors u, v, and w in the space. And so the dot product of u with the cross product of V and W gives us what we call here the triple scalar product. The triple scalar is actually what it says. It's a number. Notice that the cross product, the result of that will be a vector. But the result of the triple product, the triple scalar product, is a number or a scalar. Here, the triple scalar is no more than the determinant of the 3 by 3 with vectors here, u, the first row, vector v, the second row, and then vector w, the third row. The absolute value of this triple scalar product is the volume for a parallelopipe. Now, we see how that's going. Here, you have v and w within the plane, and then it's perpendicular, which is this cross product, which actually gives you the height. So, and what actually gives you the height is the norm of that, right? And so here we have this this base area, which is the norm of the cross product of V and W, and I misquoted. Here, to get the height, we need the projection of U onto the cross product of V cross with W. So this cross product of V and W is some kind of space, it's some kind of perpendicular space. And so then the projected image of U onto this perpendicular vector gives you, the measure of that gives you the exact height of the parallelopipe based on the coordinates of V, W, and U. So now, I hope it's okay, but I'm going to do a little drinking. It's not good for a preacher to drink, but I need some help to try to keep me going here. So I'm going to drink a forbidden drink, and I'm going to put it on video. So, and I'm sure you'll tell. So it's not good for you. Bad drink, but it helps me stay up, especially trying to record all these videos, right? I feel like Mean Joe Green. Some of y'all may not know who that is, but so let's see. I want to be able to show you that the volume of the parallelopipe is indeed this the absolute value of the dot product of U with the cross product of V and W. The volume is supposed to be the height times the base. Well, we need to get the height. We got the base area, right? It tells us that right here, right? The base area is this. The height is this projection. The height of the parallelopipe is given by, look here at the image, is the projection of U onto the cross product. It's the projection of U on the cross product of V with W. Just have to make that bigger, I suppose. Now, based on the previous section and how this was defined in the formula, that this is the dot product of U with V cross with W all over the norm of V cross W to be squared. And then this is times here V cross with W. Okay. Now understand that when you talk about the measurement of something, the length of something, it's the magnitude. And to be able to calculate that, we must calculate the norm. So the height here of the parallelogram is given by, I need to say here, the norm of so thus here the norm of the projection of U onto V cross W is equal to, here, this is the norm of this statement here. Now, this norm downstairs to be squared is a number. So the number within a magnitude is just extracted as the absolute value. So it maintains its nature. So this is equal to, here, this numerator is the number. So this is a dot product. The dot product is a scalar. So it just becomes the absolute value. So this is now times the norm of V cross with W divided by, here, the norm of this term squared. Again, the norm of this guy squared, here, that's just a number. So, and it's already positive, so we just leave it the way it is. And so this just becomes, maybe I can put it here, this is just the absolute value of U dot with V cross W divided by the norm of V cross W to be squared. So what is this? This is the height. So this is the height of the parallelopipe. Absolute value of U dot with V cross W divided by the norm of V cross W. Now the base is equal to the norm, look at that, the base area is equal to the cross product, right? The norm of the cross product of V cross with W. It's given right there, right? If you multiply the height times the base area, that gives us the volume. So the base is the norm of V cross W, and this is times, here, the height, which is the absolute value of U dot product with V cross W all over the norm of the cross product of V and W. So now do you see that the volume of the parallelopipe is the absolute value of U dot product with V cross W? That's the proof. So we've actually shown the proof for the volume of the so-called parallelopipe. Now, why do we do this in mathematics? And you say, why am I doing this to you? Well, because mathematics has to always answer the question why. We do not accept a formula for face value. But I must see where it comes from. Does it make sense Is it well defined? And if it is, then you can understand it. If not, we don't accept anything what anybody says at face value. They give us numbers. We have to be able to show with rigor, if necessary, with empirical, mathematical processes of how we got from here to over there. Must make sense. And so mathematics is the science of always asking the question, why and where did it come from? And can you show me, or can I show that it is true? And if that's the case, then anybody in the world can use it. And that's why the math is so strong, because physics, chemistry, political economy, economics, finance, managerial science, all concepts and aspects of science and nature use as its foundation the theories and the axioms and corollaries and lemmas and postulates, definitions and properties of mathematics. Let's look further. Now let's do what you like to do. That is, let's work a problem. Okay, too much talk. But good talk is good. Here, find, oh, the time is getting past me. Find A, the cross product of U and V, and then reverse that, the cross product of V and U, which is just the negative of A, and then C, the cross product of V with itself, which is supposed to be 0, according to the properties that we had earlier. So let's see, part A. Let's find the cross product of U with V. So it's written as the determinant. Here the first row is I, J, and K. The second row is the terms from U. Look, this is -2, 4, 0. These components, 3, 2, and 5. So we put the -2, the 4, the 0 there, the 3, the 2, and the 5. Now, according to our schematic scheme, this is I minus always, right, parentheses, J plus parentheses, K. Take the ith position, delete the ith row and column. We do the determinant of the submatrix of these 4 elements. It's the cross product, cross multiplication with the other direction is minus. So it's 4 times 5 is 20 minus 0. So we just get 20. Come here to the jth position, delete the jth row and column. It's -2 times 5 is -10 minus 0. Come to the kth position, delete the kth row, delete the kth column. So this is -2 times 2 is -4 minus 12 is -16. So the cross product of U and V is 20I plus 10J minus 16K. Now, it's up to me. I'm finished with this problem because part B, the cross product with V and U, is just the opposite of that according to the property. So this is -20I minus 10J plus 16K. Part C, the cross product with the vector in itself is 0. Well, I'll show you. So part B, V cross with U. Well, the vector V, 3, 2, 5, and then U, -2, 4, 0. Again, I minus parentheses J plus parentheses K. So delete the ith row and column, so we get 0 minus 20. For J, delete the jth row and column, we get 0 plus 10. For K, delete the kth row and column, we get 3 times 4 is 12. Minus a minus is positive. 12 plus 4, 16. So this is negative 20i minus 10j plus 16k. See, I told you. I told you. I keep on telling you the man is alright. Okay. You may be asking, who's the man? So the cross product of V with itself is I, J, and K. Well, it's supposed to be a K. So V is 3, lazy 3. 3, 2, 5, 3, 2, 5. Now it's supposed to get 0 according to that property. So let's see. Delete the ith row and column, so we get 10 minus 10, 0. For J, delete the jth row and column, we get 15 minus 15, 0. For K, delete the kth row and column, we get 6 minus 6, 0. And nothing from nothing leaves nothing. You gotta have something if you want to be with me. Ooh. Okay, so fine, I gotta have something to amuse myself. I'm sitting here doing this stuff and nobody's here. So find the cross product of u and v. Oh, this is good. And show that it is orthogonal to both u and v. How do you show that vectors are orthogonal? You take their dot product. So first, we find the cross product of u and v. This is 2, negative 3, 1, 1, negative 2, and 1. So J. So I minus parentheses J plus parentheses K. Delete the ith row and column. We get negative 3 plus 2, right? Minus this minus. So negative 3 plus 2, negative 1. For the jth position, delete the jth row and column. We get 2 minus 1. We get 1. For K, delete the kth row and column. This gives us negative 4 minus this minus is negative 4 plus 3, get negative 1. So here we have negative I minus J minus K. Now we need to show, and you can write this if you want, as negative 1, negative 1, negative 1. So need to show that the dot product of u with the cross product here gives us 0. Now this is not, and understand that this is not the triple scalar, if you will. Well, in a sense, you could think about it like that, but remember, this cross product here was in terms of I, J, and K, and for the triple scalar that we'll get to, it's in terms of all 3 vectors listed as row vectors. So a little bit different, but the concept is there by all means. So but anyway, let's work this the way we have it. So here, this is u cross with V. I'm just going to go ahead and list it. So U is 2, -3, 1. Take the dot product with that and this cross product. -1, -1, -1. So this gives us -2 plus 3 minus 1 gives us 0. And that's how it's supposed to be, because the cross product is said to be perpendicular to the vectors by which it was formed, U and V. Likewise, we show that the dot product of V with the cross product of U and V is also 0. So here V, no. So V is 1, comma, -2, 1, dot product with the cross product, -1, -1, -1. So here we get -1 plus 2 minus 1, we get 0. Find a unit vector that is orthogonal to both U and V. That's the cross product, right? Now, I'm going, here's where I'm pulling everything from. Well, I did talk about the scalar, triple scalar product. Just hadn't worked the problem, but we did talk about it. I didn't want to get ahead of time. We're using this theory that the cross product of U and V is orthogonal to both U and V. See that? And that the norm, or the magnitude of U cross with V, is the area of the parallelogram. But this number 1 is the one that we've been using more so. And you remember that previous problem there, we had the cross product, they reversed it, we got negative, and then the cross product of the vector with itself was 0. So we just showed that these properties are indeed true. So here, so the vector that's orthogonal to both vectors U and V would be its cross product. The cross product of U with V, this is I. Then it says find a unit vector. So that's a little bit more. So here, this is 4, -3, 1, 2, 5, and 3. I minus J plus K. So we first delete the ith row and column, so we get -9 minus 5, -14. For the jth position, delete the jth row and column, so we get 12 minus 2 is 10. For K, delete the kth row and column, so we get 20 plus 3 plus 6 is 26. So here this cross product is -14I minus 10J plus 26K. So here they want you to find a unit vector that is orthogonal. We'll call this orthogonal vector that's a unit vector. We'll call it N. And N just represents normal, and norm means perpendicular. That's perpendicular to both U and V. So here N will look like the cross product of U and V divided by the norm of U cross with V. So the norm of U cross with V is the square root of each of the terms squared, -14 squared plus -10 squared plus 26 squared. That gives us, on our calculator, that gives you 18 times the square root of 3. So here we have the -14 divided by 18 square root of 3, comma, the -10 all over 18 square root of 3, comma, the 26 over 18 to the square root of 3. Now we simplify that by all means, so this gives you a negative 7 over 9 times the square root of 3, comma, a negative 5 over 9 square root of 3, comma, 13 over 9 the square root of 3. That's it. Here, find the triple scalar. Yep, just like saying that, right? This is one good word that I can say, right. So here the triple scalar, so u. The dot product of u with the cross product of v and w. It has as the form, you put the u in the first row, then v in the second row, then w in the last. Now I was able to get this quickly by expanding along the third row, and because it's 0 there, those terms go out. Then it's 1 times delete this row and column, so you get 1 minus 2. And I was able to get the answer very quickly. But anyway, this is fine. So here, we just do it the way we've been doing it. And I'm so crazy. I don't have I, J, and K anymore, right? I got 1, 1, and 1. I have to use those terms. This is that 1 goes there, minus this 1 goes here, right? Plus. Did that for I, J, and K because I, J, and K were in the first row. Then this 1 goes here. I delete this row and column, so I get 1 minus 0 gives me 1. Come here to that second position here in the first row. I'll delete its row and column, so I get 2 minus 0 is 2. And then for this 1 there, I delete its row and column, so I get 0 minus 0, 0. So this gives me 1 minus 2. That gives us negative 1. Okay. That's it. Oh, let me show you the shortcut way. If you ever have this, you can do it. So I expanded here at this 1. The signs are important. You know, this would be positive, minus, plus because of the position. This is even, odd, even. So those numbers here, this is plus, this is negative, this is plus, because this is even, odd, even. So here this would be positive 1 times that 1, right? If I expand along here for this 1 in the third row, the third column, so then that gives you 1 minus 2, right? So the 1 minus 2 is just negative 1. You get negative 1. What you got right there. Now the standard way is to typically expand along the first row. That's how we show that. But if you see that you have zeros, if you have a row and two entries in that row are zeros. Expanding on there, you're just only expanding really on that that pivot number with the number there that's not zero, and it makes life easier. But either way, it's fine. Here, the last one, use a triple scalar product to find the volume. The volume is the triple scalar product. It's just the absolute value of it. Well, we need to identify more so these vectors. So this is I plus j. This is 1, comma 1, comma 0. J plus k. This is 0, comma 1, comma 1. Somebody's calling me. This is I plus k is 1, comma 0, comma 1. So now we look at here the dot product of the cross product of V with W, which has this formula for the triple scalar. So it's the first, U is the first row, 1, 1, 0. V is the second row, 0, 1, 1. W is the third row, 1, 0, 1. Right? So we'll expand along no i's along the first row. This is minus times, this is that one there, and then plus, doesn't matter about that, it's times 0, so we don't care. So the first one, we delete its row and column. That gives us 1 minus 0, we get 1. For this one here, delete its row and column. That gives us 0 minus 1, we get a negative 1. And then this is 0 over there, so 0 times anything is 0, so no need to even calculate that. So here we get 1 plus 1, that's 2. It's already positive, so the volume is this absolute value of the, of the dot product of U with the cross product of V and W. Absolute value of 2, but it's already positive. That's it. Thank you.